So, in the previous lectures, we mostly discussed weak interactions, if you remember. And starting from today, we will be more focused on strong interactions, and we will also introduce quarks. So quarks had pockets. What is this? Why? The quarks were introduced how? Do you remember what was motivation and reason to introduce quarks? How this notion of quarks emerged? Who remembers?
There are too many particles around and somebody should
Right. So it comes from classification of particles, not just because you have many, but because people start to classify particles. When you have zoo, different animals, you start to kind of try to put them in order. So what is this classification of particles? We start to discuss with this. And first of all, let me introduce notion of hadrons. Which refer to strongly interacting particles. So strong interactions come from structure of nuclei to keep protons and neutrons inside the nuclei. And to keep them, because we scattered nuclei, we scattered different particles on nuclei, and we know what is the binding energy. We can measure what is the binding energy. And to keep neutrons, protons with this binding energy, one needs to have rather strong interactions. So it's not like atoms, because you need to keep them in small range. So what are these strong interactions? And by the way, hadrons, a name was introduced by Lev Okun later, I think in the beginning of 60s. So what are strong interactions? So these interactions are responsible for nuclear structure. They are short-range interactions. Which actually the range is determined by the size of nuclei. And as I said, they have high intensity. So that the typical coupling, and here we can say coupling between pines and the nucleons as an example, it is much bigger than 1, or G over 4 pi is G squared is bigger than 1, substantially bigger than 1, at least at low energies. Now, hadrons are classified in the following way. There are mesons and baryons. And they differ by new quantum number, baryon quantum number. So that baryons, so that mesons, let me start with mesons. An example of mesons are pi K mesons, which we have discussed, but also rho mesons, which have spin 1. And they have baryon number 0. So we ascribe baryon number 0 to these particles, and these are mesons. Baryons like proton, neutron, then I mentioned also lambda hyperon, sigma hyperon, etc. They have baryon number 1, and corresponding antiparticles have baryon number -1. So this is additive quantum number. And also one can recognize immediately that mesons have integer spin. Zero for pine and K mesons, 1 for rho mesons, etc. And baryons have semi-integer spin. Like 1/2 for proton, neutron. Actually, all these particles have spin 1/2. However, there are particles with spin 3/2. Now, the question is, why do we need to introduce some new quantum number? Is spin enough or not? Any answer? Why we introduce B? Well, this is again the question, why we introduce these quantum numbers. Can we introduce something else or do not introduce at all? Yeah?
Because maybe in processes it's conserved in such a way that spin is not.
Right. So quantum numbers I will discuss now are actually numbers which are relevant for interactions. So they describe properties of interactions, and everything you can find the origin from some specific features of interactions, like in this case. For instance, you may have the process pion scatters on proton, and then in final state has 3 protons and some number of pions, so that you match electric charge conservation. Spin properties allow this process because we have semi-integer spin in the beginning, in initial state, and again semi-integer spin in the final state. We have 3 particles with spin 1/2. However, this process doesn't exist. And non-existence of this process is precisely explained by baryon number conservation, because we are saying, so if B is conserved, then in initial state we have baryon number 1, and in final state we have baryon number 3. So the baryon number is broken. And to, in particular, forbid this process, we need to introduce some quantum number. Another example is that we have 2 protons, scattering of 2 protons, which then transform into 3 pions, for instance. Again, all quantum numbers, electric charge and spin, allow this process. However, baryon number is broken. In initial state we have baryon number 2, and in final state 0. So we introduce baryon number, which is conserved. And actually it is conserved in all known interactions. It is conserved in strong interactions, it is conserved in electromagnetic interactions, and also in the weak interactions. Still, searches for baryon number violation is one of the most important tasks these days. And extensions of the standard model, like grand unified theories, they actually predict existence of baryon number violations. So it's only these low energy interactions which you know conserve B in principle. So if grand unification exists, then baryon number is also violated. Now, very important notion which actually lead to some extent the development of strong interaction theory and introduction of quarks classification is isospin. So this is the first notion of kind of internal symmetries. Also B is also related to internal symmetries. We will discuss in the last part of the course that the symmetry which is associated or can be associated with baryon number and baryon number conservation is U1 symmetry, but we will discuss this later. So now let me discuss isospin. So isospin is related to what we call internal symmetry of nature. And this is the key step in developments of all our theory of particles. So what are experimental facts? Behind isospin. Who knows this? Again, all quantum numbers, all notions we are introducing have some origin in observations and experiment. So you can understand why we introduced some notions and why in this way, looking back in experimental results or experimental data. So what was behind introduction of isospin? It's not like just someone was sitting, oh, let me introduce this symmetry and see what happens. Okay, there are two observations. One is equality of masses. So in particular, we have equality or approximate equality of mass of the proton and mass of the neutron. Also, we have approximate equality of masses of pions. We have 3 pions, pi plus, pi minus, and pi 0, and their masses are approximately equal. Of course, pi plus and pi minus have the same masses because of CPT, and but pi 0 may have something different, but we have this equality. Once you meet some equality of masses, this should be not accidental. And something important is behind. So if you meet in somewhere that you have equalities, then you need to think, and most probably some symmetry is behind this. Second, invariance of strong interactions. With respect to interchange proton and neutron. Or, in other words, strong interactions of protons and neutrons are the same. Of course, there is still some difference because proton is charged and neutron is not charged, and there is some small difference. But as far as strong interactions are concerned, so they have the same strong interactions. How do we know this? What are experimental facts which actually tell us that proton and neutron have the same strong interactions? Some idea? Of course, we can simply, create beams with neutrons. It's a little bit more complicated, and we see how these protons and neutrons scatter on nuclei. And to measure.
The isotopes behave the same with the strong interaction.
Yeah. So this is observation of energy levels. Of so-called mirror nuclei. What are these mirror nuclei? These are nuclei in which proton is substituted by neutron in comparison with the first one. One example is helium-3. Sorry, tritium and helium-3. So helium-3 has 2 protons and 1 neutron. And tritium has 1 proton and 2 neutrons. So people have studied the energy levels. So apart from ground state of this nuclei, you can excite nuclei by just scattering of photons and to see what is the energy level, like in the atom case. And then what has been observed that energy levels are very similar. The structure of energy levels is very similar for tritium and for helium-3. There is some difference, which actually can be explained by the fact that you have here 2 protons, and here you have just 1 proton. So there are some repulsive forces here which actually affect energy levels. But at small distances, at nuclear size, strong interactions dominate. And electromagnetic interactions give just small corrections. Of course, electromagnetic interactions take over at bigger distances because these are long-range interactions. Strong interactions are short-range interactions. So, what does it mean? So, similar energy levels. So they have similar energy levels.
This experimental fact is before all the theory of quarks and
Yeah, and isospin has been introduced before.
How is the picture in people's mind when they talk about nuclei energy levels? Is there anything inside the nuclei, do they think?
Oh yeah, nucleons, proton and neutrons. So the idea is that inside nuclei are protons and neutrons. They are somehow, have this combining energy, so the energy which keeps them inside. Then you can excite, and you can develop the same, more complicated in this case, theory as the atoms, right? In atoms you have nuclei and electrons, and we are talking about energies of electrons. And here we can also find the energy levels for in this system. So, which means nuclei has also energy levels, and there's a ground state, but then we can excite, and so you have, which means that protons and neutrons in some motion, additional motion.
So in the electron sense, we know that they are excited because they radiate. So from an experimental perspective, how do we know that the nuclei is excited?
Oh, the same. So they are excited, but then they emit photons when they go to ground state.
Just like
or they can emit not only photons, they can emit pions, maybe even in more kind of probable way.
Is the spectrum really different in terms of photons than?
Oh, it's different from, of course it's different from atomic spectrum. So I think I had somewhere, maybe I will show you, I have some slides for these levels, and you will see. Yeah, it's more complicated, and it is not like regular as we saw in the case of atoms. What does it mean? How we can explain this? How we can formalize this fact so that strong interactions do not depend on if it is proton or neutron. So this means that the Hamiltonian of strong interactions is invariant with respect to substitution of proton and neutron. Proton and neutron. So, it is meant that you should write or can write the Hamiltonian of strong interactions in terms of operators of proton and neutron. Like we have Hamiltonian for weak interactions or electromagnetic interactions. And we write this Hamiltonian in terms of wave function operators of electrons and photons. In the same way, it is supposed that you should write Hamiltonian of strong interactions, but now in terms of wave functions or in terms of operators of proton and neutron if you are at quantum level. Okay? So I will elaborate on this a little bit more. Now, these two facts, which I have explained, led Heisenberg to idea of isospin So what he noticed is that he used analogy again with electromagnetic interactions. He noticed and used the fact that we have electron, which can have two polarizations, right? Say two different component projections on the third component, plus 1/2 and minus 1/2. And electromagnetic interactions are invariant with respect to change of polarization of electron. So it's the same for polarization plus 1/2 and minus 1/2. And he thought that probably proton and neutron are somehow similar to electron with polarization 1/2 and minus 1/2. So in the same way as electron, we have a single particle which has two different states. He thought that proton and neutron are just different states of nucleon. Single particle which has two components or two different states. Here we have two different polarizations or projections of the spin on the axis Z3. We can do this classification. Here we can also say that these two particles have just two different polarizations, but not in usual space, but in some internal space or isospace. So instead of spin, Heisenberg introduced isospin. And the isospin, total isospin, and the third projection in this isospace, in internal space. Just analogy to what we have in the case of electrons, for instance. So again, proton and neutron are just two different states with two different isospins. And for proton, we ascribe isospin 1/2, and for neutron, isospin, so let me write it, I proton, and I neutron is minus 1/2. So proton and neutron have different projections on the axis Z in the isospin space.
So this is I3, not I.
Oh yeah, sorry. Right, I3. Thank you. So let me write it a better way. I3. I3. And the total isospin, which is introduced as usually as A1 squared plus I2 squared plus I3 squared, and the total isospin is 1/2 for this system. Like total spin of electron is 1/2, but it may have two different projections. You can always expand the state in these two states with two different projections. Now let me elaborate a little bit this invariance of the Hamiltonian. So what I just said, that strong interactions are invariant with respect to permutation of proton and neutron. So that Hamiltonian is the same when you interchange proton and neutron. So we formalize this in the following way. We introduce transformation which actually leads to interchange of proton and neutron. So since we have two components, we have space formed by the basis formed of two states, and then an operator which leads to permutation of proton and neutron is this. Right? So that if we have proton, and proton in this space is given by 1, 0, so this is the proton, neutron is 0, 1, but maybe minus 1 here, so that doesn't matter, it doesn't play an important role. So let me use just this one. And so if we act by U on proton, let us check what we will get. What we will get is 0, 1, 1. Maybe I will not do this. So let me try to do this later. So we introduce this transformation, and if we act by U on proton, we will get neutron, and if we act by U on neutron, we will get proton. Agree? This is permutation. So you can check 0, 1, 1, 0, acting on 1, 0, you'll get 0, 1. Well, actually, we can introduce also this for electron, but this will be just a rotation in our usual space. So in the case of isosp, this is rotation in isospace. Now, what does it mean to have invariance? So we start with Hamiltonian. So let me put here invariance. Which is made of these operators of nuclear. Now we are doing transformation, which means that we have n prime, which is u times n. So that n is u minus 1 n prime. So let us insert this n, this expression for n, in our Hamiltonian, and what we will get, h u minus 1 n prime. Okay? Now, if this can be reduced to h n prime, which means the same expression for the Hamiltonian as we started with, but now in terms of n prime, transformed fields, transformed particles. So then we are saying that we have invariance. So that means invariance. Of h with respect to transformation u. Invariance means that the Hamiltonian, in terms of original fields or operators n, is the same as in terms of new transformed variables. Okay? So this is general. We will repeat this many times, this type of the procedure. So that is what is the Hamiltonian. What is invariance? Invariance means that the shape of the Hamiltonian form of the Hamiltonian doesn't change when we go from old variables or old initial original fields to transformed fields. So here, when we make this transformation, in general, you will get something different for in terms of n prime, which differs from h. Invariance means that you can reduce this to the same form. Now, so we discussed for time being very simple, just permutation, symmetry. Instead of this just simple 0, 1, 1, 0, we can use element 0, minus 1, 1, 0, which also leads to permutation of states, proton and neutron, with additional charge. Now, this is element of SU2 group. And so, in principle, we can discuss bigger symmetry. It's not just consider permutation of proton and neutron, but then consider transformations where U is a general complex unitary 2 by 2 matrix. We can also impose conditions that determinant is 1 and so special, and therefore this is what is called SU2 group, and you can study this. Like in the case of spin of the electron, the group is not just permutation of two polarization. Right? So it's SL2 in that case. So here we will discuss SU2 group. So again, what is the sense of this discussion? Eventually, you want to describe invariance of strong interactions with respect to interchange of proton and neutron, right? So that's what was our original idea. So now the idea is that probably strong interactions are invariant not only just with respect to permutation, but they are invariant with respect to this SU2 transformations. So we can actually consider that proton and neutron transform, as we are saying, transform under fundamental representation of SU2. And Hamiltonian of strong interactions is invariant under this transformation. So the whole idea is this, that we are introducing some transformations, but eventually we claim that Hamiltonian is invariant under this transformation, or not invariant. Okay? So in other words, proton and neutron form doublet of SU2, which is transformed under doublet, or what we are saying here, fundamental representation of SU2. And the idea, and then it was, of course, checked, that strong interactions are invariant with respect to these SU2 transformations. So SU2 transformation is general, there's 2 by 2 matrices. They transform, for instance, proton to some combination of proton and neutron, right? So and then Hamiltonian is invariant under these transformations too. Now, the group provides classification of particles. So, the group has SU2, 3 generators, right? Which are Pauli matrices. One of these generators is diagonal, which is tau 3 or sigma 3. I don't know how you denote this in different ways. You can denote this differently. So this sigma 3, which is 1/2, 0, 0 and minus 1/2. So this is actually operator of I3, though. This is operator of third projection of isospin. Diagonal generators, and we will discuss this later, of the group can be identified with operators of certain physical quantities. So this is what I was discussing before. We are doing mapping of some phenomena in nature to our formalism, right? And then this physical quantity, isospin, we map it onto generator of isospin group or SU2 group, diagonal generator of this group. And we will see the continuation of the kind of repetition of this story when we will go to more complicated groups. So let me repeat this. So what we are doing mapping, and then we will check what we will get from this. Eventually what we will get the same relations as between elements of group theory and something in nature. And we can check this. And this is why we are kind of confident that we are on the right track. So let me repeat. In all this formalism, diagonal generators of group are identified with operators of physical quantities. So in our case, we have this sigma 3, which we identify with physical quantity, the third projection of isospin. So this is the way we are doing mapping of something which we have observed, which comes from experimental facts and group theory. So these diagonal elements give for us classification of particles in the following way. I'm not just doing this first almost like a classical way, but we will discuss the quantum level later. So we can act by I3 onto proton. And what we will get here, I3 is 1/2 minus 1/2, 0, 0, and proton is 1, 0. And what we will get, 1/2 proton, right? It's trivial. And the same way, acting by I3 onto neutron, we will get minus 1/2 neutron. These two equations can be considered as equations for eigenstates and eigenvalues of operator I3. So these are eigenvalues. And therefore, these numbers can be considered as characteristics of proton and neutron. And this is precisely what is staying here. You see these diagonal operators, they're just made of essentially these quantum numbers of proton and neutron. Now, another example is the triplet of pions. We have pi plus, pi 0, and pi minus. And SU2 has triplet representations, right? It has all kind of representation, quartet. So this is triplet. can be considered as a triplet of SU2. So, which means that this triplet is transformed by a joint representation of SU2 group, right, which has dimension 3 times 3. These are matrices 3 by 3. And so again, behind this we always meant that our Hamiltonian, which is the function of nucleons and also pions. We can introduce this as a pion, as a triplet. It is invariant with respect to transformations, which means that nucleons should be transformed under doublet representation, since they form doublet. And this guy should transform under a joint representation. As a result of these transformations, this guy should be invariant. So which means that if you do transformations that Hamiltonian in terms of transformed fields should have the same form. So this is invariance. Now, the first projection of in the triplet is +1, 0, and -1. And this is actually what is staying in a joint representation of isospin, third projection of isospin. So it has form 1, 0, -1. Questions? Yeah.
They are doing this for the particles that they suspect that should have the same mass, more or less, but they are not. So maybe they behave together in some other way. This was the thought.
What are the particles which have different
I
masses?
mean, they were not sure if there is any other subparticle under pi or nucleon.
Yeah, so let me clarify. We will discuss this in details. For pions and for nucleons, the situation is quite clear because a proton and neutron and pions, they have practically the same masses, right? So we are talking here about symmetry of strong interactions. Electromagnetic interactions and weak interactions actually break this symmetry. And it's clear because, of course, if you transform proton to neutron, of course, you will change electromagnetic interaction. One has electromagnetic interaction, another one not, right? So we are talking here about symmetry of strong interactions. Electromagnetic interactions violate this isospin symmetry, but weakly. So in the first approximation, we can say, oh, if we switch off electromagnetic interactions, then we have exact symmetry of this type. Well, even this symmetry is not absolutely exact, as you will see, because of difference of masses of quarks. But in the first approximation, they are kind of, this is very good symmetry. So what we are saying is good symmetry. Parameters or amount of symmetry violation is very small. So here it is, say, 0.2% or something like this. But in the first approximation, yes, so we are saying this is symmetry. Now, of course, some other particles exist, and they have different masses, and we will discuss this later. And here philosophy is the following. Total Hamiltonian can be written as part which is responsible for interactions plus mass terms. You can also talk about different symmetries in interaction part and in the mass term. And in fact, what happens is that most of this symmetry actually refers to this interaction part. And this part, the second one, can break this symmetry. Well, isospin is very good, but then we will extend this symmetry and you will see how masses actually break the symmetry, which is more extended. So here it's a very small violation.
For example, in the pion case, we do not have the experimental clue about they behave the same in the Hamiltonian. In nucleons, we had mirrored nuclei and we knew that they behave similar. But we put these three together in a triplet, maybe just because they have a similar mass.
Yes, exactly.
Expect,
Exactly. Yeah, so we just put masses were measured and we put this in this way. Not only this, actually, later people studied scattering of pions on nucleons. And then they saw that it's also, interaction is the same for pi 0 and charge pi. Again, with corrections onto electromagnetic interactions.
Could it not be possible to, for example, put electron and positron, not that maybe, but maybe counts into this picture?
Oh yeah, we put, so that's coming. So eventually we will.
No, but together with other, together with pions.
Yeah, so that will what we are coming actually.
Although they have different masses.
Although they have different masses. Actually, that was that will be next step to the quark structure. Okay, here this formalism doesn't require introduction of actually quarks, right? That's simple. Now let us move a little bit further and discuss isospin and electric charge. By the way, it's very important to understand the simplest version isospin case, because then we will make some generalization. We will introduce SU3, then SU4, or even SU5, and it will be a more complicated system. But if you understand everything with this simple isospin, which is the first step, then it's easy for you to understand other things. Now let me discuss isospin and electric charge. So let's take proton and neutron. So they have third projection of isospin 1/2 and -1/2, and they have electric charge 1 and 0. So that describes isospin, this is electric charge. And you see the difference of isospin here 1, and also the difference is here. And one can suspect that somehow electric charge and isospin should be connected. So let me put here I3 and Q are connected. Let me put question mark. So maybe electric charge is the third projection of isospin plus something. And this precisely gives difference of charges, but it should be added something which actually also give the average. And this can be what? By that time people knew baryon numbers, one can try. So why not to put here baryon number over 2? This is empirical relation. And that reproduces correctly electric charges, right? Because baryon number for proton and neutron is 1, and therefore this is 1/2. And then adding plus 1/2 or minus 1/2 will produce electric charges of proton and neutron. In fact, this has a deep physics meaning, which was actually realized later. Now, let's try to generalize this to other particles. And let us consider K mesons. And as I told you, actually 4 different K mesons have been discovered. K plus, K0, which have strangeness +1, and then K0 bar and K minus, which have strangeness -1. That is another quantum number. These particles are mesons, and therefore baryon number is 0. So if we will try this formula, it will fail to describe electric charges in this system, right? Because baryon number is 0, and therefore you would expect electric charges 1/2 and -1/2. So we need to generalize this formula And this formula can be generalized, taking into account strangeness. So this is strangeness, not spin. So we can do this in the following way. I3, which is describing difference of charges in up and down components, plus, so let's keep P, also it's 0, but add strangeness. And you can find out that that formula, which is the formula with the name Nishijima and Okuba, that reproduces electric charge perfectly for this system. You can check this. So in this connection, also another quantum number has introduced Y, which is actually B plus S, and this is referred as to hypercharge. This is the definition of hypercharge, and therefore the formula for electric charge for the hadrons is that Q equals I3 plus Y over 2. Again, we will see that behind these quantum numbers there are some symmetries. And what is interesting that behind this is SU2, we have discussed already, right? And behind this hypercharge is U1 symmetry. So that this quantity, hypercharge, it is connected to generator of U1 group. Yeah?
You introduced this new quantum number, which is somehow also some conservation, implies some conservation, right?
Yes, so again, behind this everything, so what we are introducing quantum numbers and symmetries, these are symmetries of strong interactions. And therefore quantum numbers which are conserved in strong interactions.
So we had baryon number in hypercharge. Introducing a new quantum number, does this imply that baryon number or strangeness might not be conserved?
No, so they are, why? No, in strong interactions they are conserved.
So do we actually need that hypercharge? Because we had two conserved quantities and we name it.
Yeah, we can reshuffle things, and in certain respects it's better to use not this B and S by hypercharge, because here it's clear because these guys enter the same combination, and from the symmetry point of view you may want to use this Y. Okay. Now let us discuss family of the particles. The families of atoms. As we already mentioned, large number of new hadrons have been discovered in the beginning of 60s. And the first what you are doing, you are trying to find some order in this chaotic stuff. And so particles were kind of put in different groups which have similarities, and different groups have some also classification. So common properties. Common properties of the families are B, baryon number, S, spin, and P, parity. You may try something different, but I see if you get something interesting. So, family, and these characteristics are common. All the members of family have the same B, like family name, B, spin, and parity. Within the family, something which distinguishes particles and differences within family are the following. It's electric charge and strangeness or hypercharge. So this is strangeness. Alternatively, you can use I3 and strangeness. Because they are not independent, right? So you can use Q, S, or I3 and S. And baryon number is the same for all the members of the family. Okay? So I will use actually I3 and S to put these famous plots of classification. Strangeness here and I3 is here. 0 minus 1/2 minus 1 and this is 1/2 and plus 1 and strangeness 0 1 and minus 1. So let me consider the family of particles, mesons, with spin 0 and with parity minus 1. This is parity. So this is the spin, and baryon number is 0. So that's are the quantities common for all members of the family. And parity actually tells you how the wave function is changing when you do reflection of coordinates, space coordinates. Minus 1 means that under this reflection of coordinates, the wave function acquires minus sign. So there are 8 particles found with these properties, and let me put them. So what? These pions. Let me start with pions. Pi 0, then pi minus, and here pi plus. They have 0 strangeness, and they have isospin 1, and therefore third projection of isospin is minus 1, 0, and plus 1. I put this in these positions. Now, K mesons. We have 4 K mesons. They have strangeness K0 and K plus have strangeness plus 1. So I put this along this line. And they form isospin. They form isoduplet. And therefore they have third projection minus 1/2 and 1/2. Now K minus and K0 bar are sitting here. So that here is K minus, and here is K0 bar. There is another particle, eta meson, which has 0 strangeness and 0 isospin. And it doesn't form, it has trivial multiplet, right? It's single, so it's sitting here, it has no companion. The rest can be combined in the following way. And then you have this nice diagram. And how many components? It's easy to find that there are 8 components. You see, isospin is embedded in this picture, right? So these particles are, quantified by isospin, the third projection of the isospin. And you have this third projection, and S, also strangeness, is involved. And we get this nice picture. And I can say in advance that, of course, masses of these particles are different. Masses along this line are very close to each other. By the way, eta is different from the mass of the pion. But the masses of K mesons, and we have already explored this study, are substantially different from the masses of pions. So, although they form the same family, masses within the family are also quite different. We will come to this question. And now let me write another family, to show you another family, which is the family of baryons. You know baryons. Again, I have S and I3. And now I will use S0, -1, and -2. It is not symmetric because for this family I can introduce anti-family. Here there is no anti-family. Particles and antiparticles are sitting in the same family here. For baryons it's not the case because they have another quantum number, baryon, right? And for baryons and antibaryons we have plus and minus, and therefore they form different families. Now, so let me show the isospin. So projection is 1, 1/2, 1, 3/2, -1/2, -1, -3/2. And so we have proton and neutron, which form isospin doublet, right? And they have third projection -1/2 and +1/2. So we put them here, neutron and proton, and they have strangeness 0. Now then we have triplet of sigma hyperons, and this is sigma minus, is sitting here. Here is sigma 0, and here is sigma plus. And also there are eta particles, doublet, which is sitting here, so it's eta minus, and at plus, 0, sorry, minus at 0. Here's plus charge and 0. And yet another member has been found, which is lambda hyperon, which also has the property, it has no companions. It's a singlet of isospin. And so it's sitting here. And in the same way as before, we can connect the particles on this diagram in this nice way. So here we deal with, again, octet, 8 components, octet, of baryons, B equals 1, and spin equals 1/2. So all these particles have baryon number 1, spin 1/2. And for baryons or for fermions, we are not introducing parity because it has no sense. I will discuss this later. That is just characterized by these two quantities. And of course, there is also octet of particles with baryon number -1, which contain antineutrons, antiproton, and anti of these particles. Okay? Questions? So this is really emerges from experimental fact, from observations, from the fact that we have observed these multiplets. Of course, some other particles have been observed, and they form other families. And there are families of particles with spin 3/2, for instance, baryons with this, and also some families of mesons.
The strangeness of these sigma matter particles, they come from the production, so we try to match the strangeness in the production process.
Yeah, so how you asking how it was determined? Yeah, so these particles have been discovered, and to match strangeness conservation and strong interactions, we need to ascribe to this lambda this quantity -1. Partially it's scattering, I think it's production. They were produced together with K mesons, and therefore to have conservation of strangeness, you need to ascribe this -1. Actually, I have written one of these reactions. It was even before. And actually, lambda also decays, or this sigma decay with emission of K mesons, and therefore it's clear to have conservation. You need to identify with this quantum number. So quantum numbers, yeah, were obtained, assuming that they are conserved by strong interactions. Okay, so let us move further. We have this picture, and then what was interesting, so why particles form these octets, if this is accidental or not, or maybe there's something interesting behind this structure. And developments were what we called eightfold wave. Worked out by Gell-Mann in particular. And we will see that this eightfold wave, this is because 8 particles in the multiplier, so the families were observed with the number of particles 8. This what led us to SU3 group. To extension of SU2, because isospin is within this picture, so that leads essentially to extension of SU2 group to SU3. You want to ask something?
Yes, the isospin discussion on this family of octets, could we also put up the other isospins together? Like we know that from the mathematical discussion of SU3 that we can take slices of SU2 from those 8 particles if you take the right 3 among them.
So I'm not sure that I understand what you want to do.
I mean, we have the triplet, pi minus, pi 0, pi
Yeah.
plus. It was sitting in the octet. So there was another choice of triplets that we can do.
Including pines.
Without pines, like we can take a cow, a pion, and...
No, but we established that K meson has isospin 1/2. We cannot.
So you can't
everything. That's fixed actually. Okay. We have found 4 K mesons instead of 3 pions, and then we introduce another quantum number for these particles, which are strangeness, and we don't want to confuse strangeness 0 and strangeness non-zero.
So all isospin discussion was fixing, defining the pion triplet and 2 count doublets.
Yes, yes. So they were observed, quantum numbers were identified. It also was this idea that strong interactions are invariant with respect to, actually we have now 8 particles, and philosophy again the same. So we can generalize this SU2 symmetry group, and now we have more particles, and we can make some transformation of these particles, and the idea is that the strong interactions are invariant even under this more extended symmetry group. So that's what we are coming to. So, so we have these octets, and let me denote the octets by M. Don't confuse with the mass, but so it's always difficult to find so many notations to everything. And now the idea is that the group which is behind all this physics is bigger than just SU2, and we will denote this group as F. So it's a flavor group. what we call now flavor group. And this G, the group and the symmetry, is the symmetry of strong interactions. And the philosophy is the same. We have Hamiltonian of strong interactions, which is some functional of this M. And this is our octet. And actually, several octets. We have baryon octet, we have a meson octet, and so we need to put everything here. And now what we are doing, as we did before, we introduce symmetry transformations so that M prime is V, this is transformation, acting on M. So we introduce these transformations. M is our multiplet, octet in this case, and this is the matrix of transformation, which in general should be 8 by 8 matrix, right? And then the idea is the strong interactions are invariant with respect to these transformations, which means that if you put instead of M, expression in terms of M prime, which will be V, G minus 1, M prime, then this can be reduced to H M prime. And so that means symmetry. So which means that we have Hamiltonian, then we do transformations of the fields which are entering these Hamiltonian operators using these 8 by 8 matrices, and still we get that the form of the Hamiltonian in terms of new variables is the same as before transformations. Now, what is this symmetry G? Let's try to identify what is the symmetry, what it could be. So it should have representation 8 because we have octet of particles, right? So this V is the matrix 8 by 8. SU2 has representation 8, right? SU2 has all possible representation, 1, 2, 3, 4, 2, 3, 4, 5, etc. But SU2 doesn't work because then in octet we will have the charges, say 0, minus 1, minus 2, minus 3, right? So that doesn't work, first of all. Second, using this, so constructing these octets, we actually use two quantum numbers. That was I3, and that was strangeness. So what I was saying, so these are physical quantum numbers, right? Strangeness, quantum numbers, right? And isospin. Doing this mapping onto group theory, we need to have the group which has two diagonal generators, right? Which has rank 2, not just 1 like SU2. And therefore SU2 certainly doesn't work. And the simplest way is to try SU3. SU3 group has two diagonal generators. And we can probably try, against this trial always, and to see, we can see what will happen. As the symmetry group, this GF. So GF is SU3. Have you studied SU3? Or a little bit, right? At least. So you know something. So it has two diagonal generators, it has rank 2. So let me remind, yeah?
Yeah, but definitely with adjoint representations, because you can have higher representation. So we specify it to adjoint.
Yes, I'm just coming up. I will tell you. So this SU3 has representation 8. We know this, right? So that's adjoint representation. So let me just say what are these properties of SU. Remind you. So it has fundamental representation 3. and also 3 bar. So we have 3. So we can construct higher representations of this group, in particular using the product 3 times 3. So it has 9 components, and it can be expanded into irreducible representation in the way A plus 1. Right? We can use 3 times 3, which again has 9 components, but since here we have conjugate, here not, and this is expanded as 6 plus 3. So it has representation 6 and it has representation 3. And finally, and we can of course continue this, we can use the product of 3 representations. So it has fundamental, it has 27 components, which can be expanded as 10 plus 8 plus 8 plus 1. So the idea is that probably these octets which we are observing, I'm just repeating, are transforming under a joint representation of SU3 symmetry group. And so the symmetry of strong interactions is actually not SU2 but SU3. And when you are doing these transformations, at least part of the Lagrangian which describes interaction is invariant. Clearly masses are different, and so clearly part which are giving for us mass terms breaks the symmetry. Right? In the symmetric limit, you would expect that all particles have the same mass in the same multiplet. But since this is different, now we can promote the idea that only the part which is responsible with interactions, that part is invariant. And mass terms have some other physics behind, and they break the symmetry. So this is now philosophy, how we make all these generalizations. Now with this type of the expansions, we have 2 immediately questions. The first one is, we have, apart from octets, we have representation 3, 6, and 10. So where are these representations? Do we have particles with these multiplets of particles? And the second question is, where is the fundamental? Representation. So we have octets, and then the question is, if you really take seriously this group, as a symmetry group, we need to explain why there is no observed particles in this representation 6, in representation 10, or why there is no fundamental observed. Why I'm repeating this, probably I mentioned already before, because nowadays people are introducing, in attempt to explain masses of leptons and quarks, introduce also flavor symmetries, different from this. And they use some representations, not even the lowest, but some representations, just pick up. And don't ask questions why there is no particles with lower representations, for instance. This is an example which tells you that nature doesn't like to jump. So nature doesn't like, say, to use only one representation A here, dot. We will see that actually nature uses all these representations. And the fact that we do not observe, at least in the first place, these particles, actually has deep physical meaning. It should be some good reason for the fact that we do not observe some representations. We do not observe 3-plet, and we don't observe 6-plets. And you will see that actually all the dynamics of strong interactions is behind these questions. Now with 10-plet, things are quite simple. And the point is that already in the early days, the 10-plet of particles has been observed. So let me represent this. So those are the particles with spin 3/2. and baryon number 1. So let me again write for you diagram with S and I3. And strangeness involved here is has the values 0, 1, minus 1, minus 2, and minus 3. Now the isospins are 0, 1/2, 1, 3/2, minus 1/2, minus 1, minus 3/2. And now the following particles have been observed. Quartet of delta particles, delta resonances. Delta minus with isospin minus 3/2, delta 0, delta plus, and delta plus plus. So you see, the baryons have been observed with double charge, you know. And these 4 components form the isospin multiplet with isospin 3/2. Okay? Now, apart from this, particles with strangeness -1 have been observed, triplet. That is sigma minus, but these are sigma which differ from sigmas which I have discussed before. Those have spin 3/2. And people are writing 3/2, but I just do not to make it to messy picture omit the spin. Then there were particles eta. Again, they differ from eta which enter the multiplet with a proton. And what you can find here that there are 9 components. So that's what has been discovered. Oh, I think I did some. No, it should be. Sorry. That should be here. So sigma plus is here. Sigma plus and yes. So we can combine them, and what you will get is this picture with 9 components. 5 here and 4 here. And then it was observation. So if we really seriously believe in this SU3 flavor group behind, it should be another component, and it should sit down here with strangeness -3. And what was amazing, this particle has been discovered. So that was really strong confirmation of this SU3 picture. So that has been discovered after already this classification method. And that was a really serious confirmation of SU3 symmetry behind. Yeah.
Those sigma and I don't know the name of that letter. They are the spin 3/2 versions of the same particles because they form another.
This is why they actually have similar notation because at least for the isospin they have.
But the quartet is from spin quartet. They form a spin quartet, but if they form an isospin triplet.
So so they have a spin 3/2, but they form isospin triplet. Yeah.
So does it matter in which order that you put the particles? Because for isospin, it's an abstract spin and we cannot observe it like spin. So.
Well, we observe isospin, a kind of as well as usual spin. What do you mean? We have proton and neutron. So hold this story. Let's come back to the beginning of lecture. So we have these experimental facts, proton and neutron, which have quite similar masses, and they have the same strong interactions, which means that strong interactions are invariant under SU2 transformations in general. So this is already proved. So what's more?
But there was no reason to choose proton as plus 1/2 and neutron as minus 1/2, or to put all the deltas in order.
You will get the same. You can renormalize. You can substitute plus by minus, but then you need to change the signs everywhere because they were identified in conservation laws. You need to explore the different reactions, and their regularities give you connection between isospins of different particles, like isospin of meson and isospin of baryon. Of course you can change, but this is matter of notation, right? Or you can use operator sigma 2 written as minus 1/2 in upper part and plus 1/2 in down. That would be equivalent.
As we put it on the diagram for octets or templates, we should pay attention in which order we write.
Well, again, so physics doesn't depend on this. This is matter of notations. Again, if you start to change some plus to minus, but then you need to change in coherent way, in the same way, all other charges of prescription. And then you will get the same picture. Electric charges are measured. So you can draw these diagrams not using not isospin, but electric charge. If it's more common for you, right? So I use this isospin third projection S, but you can use instead of this electric charge.
But if I use electric charge, then I have a reason to put things.
And you will get the same picture.
Same.
Yeah. Well, it may be because they are correlated, so the S enters. I don't know. The maybe picture will be slightly different, but you will get the same connections. So, yeah, that's for today. And there's more questions.
Which one is the particle?
This is omega. It's omega and it has double charge, I think. No, it has one charge, this is minus. Very important particle. We will come back to this particle when we will go to quark structure. Well, I can write this in a different way, in this way, if you want. Omega. Okay? So now, homework, you can give it to me, then I will bring for you, but maybe next time you can give it immediately to Takeshi. Again, look back to this lecture and think if you do not understand something, because then things will be kind of accumulated and we will move even faster. Okay, and then I want to discuss with you, right? Oh.
Is it okay if I give it a
Well, yeah. Then he will mark this. I don't know if it will affect what he will put you eventually. Great.
sacrifice one. You sacrifice yourself to thank you. I bring all my sheets. That one? Yeah, because it was everything was in proper size. You want the map of Torino? Oh no. Yeah. Oh no. Yeah. Oh
Business from presence. It's fine.
You don't know
I think
sure.
this one. I think it's fine.
yeah.
I hope so.
And
They use the
sì, sì, questa chiesa vicina is blue. But it's white, but it's lightened by blue light. So in the night, you just see a shiny blue church. It's not
But actually, we only have to test here. So if you want to leave your things there, it is no problem for us. We only have to test the computer and the screen. No problem, okay? Thanks.
There's the console.
Here's the screen.
It's like streets. They would use the yeah. Is 60 kilometers inside the city. So you can see it from above.
So on.
Shining very straight line.
Oh,
how strange this is.
There.
Dovrebbe sintonizzarsi già. Anche questo forse, questo qui. Sono loro, sono i tecnici. Ah, guarda qua.
Ah, okay. Ah, for video recording. No, we don't want to video record. Okay. Okay, there it is.
Yes.
Good. So,
The lights
the
are
lights,
here.
yeah, should be perhaps.
Okay.
Uh-huh. Well, let's put something lighter, like a normal page. Okay, good.
Internet là.
So this is easy. Username and password we know. So this everything here, everything works. And obviously here we will have the question in case
Ah, nice.
there
Look
is
at
a
this.